In the spirit of stepping back and evaluating our models, here we'll ask, is our model strong? For example, consider the high peaks data, which includes information on hiking trails in the 46 high peaks in the Adirondacks, a mountain range in northern New York State, shown on the map over here. Notice that the completion times vary from trail to trail. Here we see data on just 4 of the 46 peaks. Some trails here take more time in hours to complete than others, so 10 hours for Mount Marcy, up to 15 hours for Mount Skylight. Our goal here will be to understand why. That is, why do some hikes take longer than others? Consider 4 possibilities. We could model hiking time by the highest elevation in the hike, by the vertical ascent of the hike, that is, how many vertical feet it covers, by the hike's rating, whether it's easy, moderate, or difficult, or by the total length of the hike in miles. Now suppose that you could only pick one of these 4 potential predictors of hiking time. Which would it be? That is, which predictor would produce the most useful or strong model? To this end, elevation appears to be the least useful predictor. It exhibits the weakest trend with hiking time. In contrast, the hike's rating and its length both appear to be strong predictors. The more difficult the hike, or the longer the hike, the more time it will take to complete. Now, evaluating and comparing the strength of our 4 models using these visualizations alone leaves a lot of room for subjective interpretation. As such, we'll typically complement our visual observations of model strength using the RSquared numerical summary. For example, the relationship of hiking time with elevation has an R-squared value of 0.0003. Further, the R-squared is 0.22 for the ascent predictor, 0.65 for the rating predictor, and 0.74 for the length predictor. This range of R-squared values reflects the fact that R-squared must always take on values between 0 and 1. At one extreme, we see that the closer R-squared is to 0, as with elevation, the greater the observed residuals and the weaker the model. At the other extreme, the closer R-squared is to 1, as with the length of a hike, the smaller the observed residuals and the stronger the model. In fact, an R-squared value of exactly 1 would correspond to a perfect model for which every observed data point falls exactly on the trend. Further, these R-squared values have a meaningful interpretation. They're not just numbers between 0 and 1. Rather, R-squared measures the proportion of the variability in the observed y values that's explained by the model. Similarly, 1 minus R-squared measures the proportion of the variability in y that's left unexplained by the model. Let's get some practice here with some examples. For example, the length of a hike explains 74% of the variability in completion times from hike to hike, or 74% of the differences in completion times from hike to hike. The other 26% of these differences is explained by other factors, so factors such as the vertical ascent, the elevation, the difficulty, weather, and so on. At the other end, a hike's elevation explains only 0.03% of the variability in completion times from hike to hike. Or basically, knowing the elevation of a hike really doesn't tell us anything about how long that hike might take to complete. Finally, I want to connect R-squared to perhaps a more familiar concept, that of correlation. In the very special case in which we're modeling y by one quantitative predictor x, we can also measure model strength using correlation. In fact, in this case, R-squared is equal to the squared correlation. But correlation is very limited in its usefulness. It can only be used to measure the strength of a linear relationship between y and one quantitative predictor x. It cannot be used to evaluate nonlinear models or relationships, models of y by one categorical predictor x, or models of y by multiple predictors, whether they're categorical or quantitative. Yet R-squared can be used in all of these settings. Given the constraints of correlation and the flexibility of R-squared then, this is the last we'll say about correlation. From here on out, we'll measure the strength of our model using R-squared.